spending the time with me. We have a very packed agenda. I will try to get it done in less than an hour and a half. I know we have an hour and a half scheduled. But thank you so much for spending your time with me, especially on a Friday. I know some of you were with me last Friday. We had some folks from most continents, including Brazil. I don't expect the Brazilians to attend this call, but we'll record the webinar and we'll send it out to you. Couple of things, just housekeeping items. If you have a question, click on that Q&A button on the webinar, or click on the chat button. I'll be able to see either one. We can kind of go through the questions live. Let me get started right off the bat, just because we do have a lot of content to cover. I'll do a brief introduction to some of you. This may be repetitive if you've attended a session with me before, but let's just kind of cover it for those folks that may not have haven't had the pleasure to meet. And so my name is Armin Kakash. I'm the founder of Revology Analytics. And so quick background on me: spent most of my time post business school in revenue management and analytics. So started revenue management teams, built analytics teams, but it was really sort of this whole area around revenue growth analytics that I've done for the last 12 to 15 years or so. That's kind of my path. Founded Revology Analytics in 2022, exclusively doing revenue growth analytics consulting, mostly for CPG manufacturing and distributors. That's really kind of the specialty of and quite frankly my interest, as well as the industries where I think pricing has a lot to grow. About Revology, so I talked about it's exclusively revenue growth analytics firm. So what does that mean? It's really, think about it as a sort of a analytics heavy revenue growth management advisory firm. And also kind of dealing with some sales analytics and optimization areas as well. Why did I establish this company? I've noticed a lot of challenges in most industries that I've worked in, as well as some of the industries that I've done some advisory work around. One, there's analytics are taking way too long, right? Long cycle analytics, it's a big problem. I think most companies assume they need multi-million-dollar and 18-month solutions to solve their key profitability and pricing and customer analytics challenges. The reality is you don't in most industries, particularly mid-market industries. Simple mechanisms and sort of popular tools that the companies have, you can actually build these solutions, especially if you involve the key stakeholders from the companies to drive adoption. So I think it's one of the big misconceptions in industries that I've seen. Price setting is really suboptimal. It's also very manual, right? So most companies can actually use some automation. And again, it doesn't have to be complicated, but you can create some sort of rule-based dynamic pricing that'll save a lot of money for companies and certainly a lot of human labor. Promotions and marketing efforts, but especially promotions and rebates, for most manufacturers, most distributors, they're profit eroding, right? They're highly negative ROI. In fact, most companies don't actually have the capability to measure the ROI of their promotions. And again, there's simple ways to sort of set that up. We talked about pricing processes are manual, and there's limited sales and customer insights. I remember when I was sort of a functional executive for companies, it was really hard to get the insights at my fingertips that enables me to make the right decision at the right time. It took days and weeks, and everything had to be recreated. So it's a big sort of an issue that is plaguing most companies. And so companies that actually have these capabilities, at least foundational sort of revenue growth analytics capabilities, they outperform their peers, right? And that's not a surprise. They outperform it both in terms of sales volume as well as operating profit. And so having sort of been at the functional practitioner level, as well as the commercial executive level, I sort of understand the nuances between doing the science, marrying up with the art of collaborating with the organization, especially sales teams, et cetera, to make this happen. Quick personal note about me: we live in Charlotte, North Carolina. I'm originally from Eastern Europe, and so that's my family. They're way prettier than me. My wife Ashley, 2 kids, Cameron and Chloe. And so in my free time, the limited free time that I do have, I spend time with them, play with my kids, and I read books, right? So I'm a huge sort of analytics, machine learning, and pricing nerd. So you'll see some of my books. The reason I included this in this Miro environment that you see. I know it's a little bit strange for most of you, are probably used to PowerPoint. You can actually zoom in. You'll have a copy of this content. You can actually zoom in and like see some of the titles and some of the authors that I'm reading. I tend to read like 20 books at the same time, and take like 6 months to finish. And so there's just part of my library, but I included it for you. One is a kind of a personal touch, but two, if you find some value in it, you can probably just leverage it. Outcome-based analytics process, I'm not going to spend too much time, but this is typically kind of the framework that I tend to follow. And so the philosophically, really the concept here is focus less on the technical sophistication, even though we'll actually go through some sophisticated stuff this afternoon, but focus more on the outcomes, really understand the problem, be able to sort of split those problems into components that you can actually address and be able to prioritize. And most importantly, work with your stakeholders and bring them along the creation journey, right? Because otherwise you won't have adoption of anything that you're creating, right? So it's really this idea of focusing on the outcomes as opposed to the technology and the algorithms, right? And that's as simple as that, right? But let's dive into the topic. So we'll talk about price elasticities. We have an audience today. I think there's many of you that have joined. Some are more advanced than others, right? So I'll try to talk about the stuff that we're going to go through, especially when we go through our code in the next probably 15 minutes or so, in simple terms, right? But if you have any questions, again, ask me those questions. But for now, I'll make the baseline assumption that most of you or some people don't know what elasticities are and why they're relevant. So I'll talk about that a little bit, and we'll go into the R coding. Don't be too sort of upset if some of the stuff that I'm showing is maybe too complex for some of you, maybe too simple, right? You'll have access to this content. You'll have access to the R code. I'll send those out after this meeting. So you'll be able to email me and ask questions later on if you don't understand, right? But what is elasticity? Very simple, right? It actually measures the change in units as a result of changing in price, right? It's as simple as that. Most often it's a negative number. Sometimes it's not a negative number, right? It's for things like luxury goods or industries that have industrial products that are heavily financed and things like that. Sometimes it's a positive number when you actually model it, right? But in reality, it's always going to be a negative number in concept, right? But it's relevant for us for several reasons, right? And I think it's a foundational capability for most companies. Some companies don't have these capabilities, but it's relevant for several reasons, right? One, it actually helps us increase our price realization, right? It helps us actually increase the ROI of our marketing and our promotional efforts, because we understand both in terms of our price adjustments as well as our pricing discounts, what the impact is to our business, what the most efficient or the most best ways to promote it by product, by customers. So it actually helps us do those things. It also minimizes pricing risk. It allows us to run some scenario analysis when we want to make some important price changes, or when we want to do our annual price increase efforts, right? So it allows us to run those scenario analyses, very relevant for certainly finance teams, of course, for revenue management teams as well. Optimizing inventory and really ensuring that you have enough liquidity in your companies. It's important. Many companies, especially again, manufacturers, distributors, they buy more stuff than what they can sell through. So you have product that's just gathering dust in the warehouses over several months, and sometimes in excess of 2-3 years. And so knowing what those elasticities are helps you actually design some clearance pricing efforts that help you sort of optimize your inventory. Driving net sales and gross margin, right? We talked about this aspect of running scenario analysis and be able to adjust pricing and discounts in a way that drives more revenue and gross profits for your company, and is really the foundation for most price optimization capabilities, even still today, right? We can talk about price optimization later on, but just know that price elasticities and cross elasticities, for the most part, they're still sort of the baseline of most price optimization solutions, despite people sort of talking about AI and things like that. Okay. Let's move on to the next one. Typical variables, and we'll talk about this when we go through the R code, but pricing is obviously one. You can have several forms of how you define pricing. You can just sort of measure the average price. You can measure the regular price. You can certainly add promotional price as one of the variables as you're trying to estimate price elasticity. A really good practice is to actually base this on relative pricing. So your price index to the competitor price, it's sort of an accepted practice. Why? Because most businesses, most consumers, right, they react to changes in relative price, not necessarily in changes in terms of your absolute price. If you raise your price by 5%, but your competition raises by 10%, you're still cheaper, right? So the effects may be dampened, right? So that's always a good practice. Merchandising variables relevant for B2C industries, especially so consumer products, but really anyone that is sort of a consumer-facing industry that relies on discounts, displays, advertising, coupons, things like that. You want to include those variables. Seasonality is really relevant among most people. Don't include that, but that's important to actually include in our pricing elasticity efforts because price elasticity modeling is nothing more than sort of creating a really strong demand model off which we can actually estimate price elasticities. You want to include some lagged unit sales. What did we sell in the same week a year ago, 13 weeks ago, et cetera, right? It's typically a good practice to include those. Interest rates, if you're selling items that are financed by your customers, if you're a manufacturer, you sell to distributors and those distributors happen to finance the purchase of the inventory and they buy more when interest rates are lower, which is a natural practice to do. You want to include interest rates in your modeling. Inventory levels, if you have access to it, and then obviously some categorical variables for things like customers, products, customer segment, et cetera, right? Going to use linear regression versus machine learning. Well, you'll see this in the modeling that we're going to go through, right? So linear regression, again, it's pretty dominant to still use linear regression for most price elasticity estimations. I think, I'd say even sort of well-known information providers, at least in the consumer product space, if you think of like IRI or Nielsen, maybe SMIS, they tend to do linear regression, which is appropriate for consumer products, but that's still kind of like the de facto method. And it's okay for some industries, but you really want to use it when there's sort of a nice linear relationship between price and unit sales. Tends to be the case on lower priced products, higher transactions and things like that, right? You also need a lot of data. You want to ensure that there's minimal correlation between the predictors, right? It's not always the case. In fact, in most industries, that is definitely not the case. You tend to have high correlation between things like pricing and seasonality and competitor prices. Machine learning, right? It's when the relationship is nonlinear, which is again most industries outside of sort of CPG and retail, relationship is going to be nonlinear. If your data is sparse, machine learning methods are typically better. If there's high collinearity, so there's variables are highly correlated or related to each other, right? It's also some machine learning methods are more acceptable. And by the way, you can apply it in all industries, and we'll talk about how to do that. In terms of your roadmap, and again, I'm going fast, you'll have access to this content, but just think about in terms of the capability roadmap for your organizations. If you don't have these capabilities today, maybe you're relying on third parties, or maybe you just don't measure price elasticities for your particular company. This is a pretty sort of standard roadmap in terms of how to approach building these capabilities in your organization. You really want to kind of start with the basics, right? You're going to do the multilinear regression, and we'll do that today. You can kind of move on to a multiplicative model, which is nothing more than, they call it a log-log regression. We'll talk about what that is, but that's, again, typically the standard in most industries. It's also very easy to interpret, which is one of the reasons people tend to gravitate towards that. If you increase your sophistication, you want to do some regularization. All it means is you're simply employing some techniques that are going to ensure that highly correlated variables, some of them will be sort of reduced, and the impact of those coefficients is not going to be as augmented or as amplified as it would be under normal conditions in a later regression, right? But there's techniques to do that relatively easily. Machine learning models. I like to use random forest models, and I'll explain why. But again, using ML models is going to be a bit more sophisticated. There's different ways to estimate price elasticities from those models. I'll show you one of those methods that tends to be good, and I think it works for most instances. But again, that's going to be a bit more sophisticated than regularization with regression models. And then if you want to combine models, right, you can actually do some stack modeling when you do maybe some regression models for your top movers, your top, I don't know, top 10 items that drive 90% of the volume. Well, the relationship is linear, and regression models tend to be maybe more accurate. For others, maybe you use a machine learning model, you can combine it eventually, right? So you're kind of creating the stack model. So again, think of the capability in your organization as a sort of this roadmap, right? And there's things in between that we didn't cover. So maybe you can put things like mixed effects models, right? And we'll talk about what that is. That's maybe in between number 2 and 3. And again, today we'll focus on 3 things. One, we'll do just a very simple linear regression model. We'll do a log-log regression model, and we'll cap it off with a random forest model, right? So again, we'll have subsequent sessions in the future where we can get into the details and some of the other methods. This is just sort of ranking of, which sort of model should you use in industries, right? So if you work in retail, it's okay to use log-log regressions, right? It's okay. You may want to apply some regularization to that, right? Because variables are highly correlated. If you work in CPG, consumer products, there tends to be very strong linear relationship between pricing and units, right? So log-log regressions are typically good enough in consumer products, right? Sometimes you add mixed effects to that, that's fine. Sometimes you can add regularization, it's fine. But again, log-log regression will give you good enough directional price elasticities that you can drive value with, right? And so typically there's sort of a false precision associated with elasticities, and that you tend to have some pretty sort of complex methods. I would say log-log is good enough if you work in CPG. If you're in distributor environment, or if you're a manufacturer that manufactures larger ticket items, right? That's where you want to get into a bit more sophistication. More data engineering is going to be needed to just make sure your variables are done right. And that's where you really want to get into some more sophisticated machine learning models or ensemble models that do a good job of handling highly sort of correlated variables. They also do a good job of handling outliers. And so it's typically a good recommended way to do that. I want to touch base a little bit on this one, because you'll see this towards the end of the coding exercise that we'll do. And this may be a little bit new to some people, right? But this is one way to estimate price elasticities using random forest models. And it's actually fairly simple, but fairly fairly elegant and useful way to do that. Why? Because you can actually get price elasticities at a variety of different levels that you want to. You can get it by price range, by time, by customer group, by product group, right? Or a combination of all of those, right? But when we build these models, and for those of you that may not have built random forest models, think of random forest models as just a collection of decision trees, right? So think of the decision tree. It's your typical sort of if then else sort of statements that you see down below, right? It's sort of similar to this, right? And so random forest is nothing more than just a bunch of these decision trees sort of averaged together, right? It's the same concept as if I ask all of you, or each of you rather, what my height and weight is after sort of meeting me in person, you guys will guess. Individually, you guys may not be that correct, but when I actually average out the answers, you'll be pretty spot on in terms of what my height and weight is, which is at least on the weight side is not very encouraging. But that's sort of the law of the average, and I think that's why machine learning models, in particularly for industries where you have this nonlinear relationship, which is most of them, is really powerful. And so, how do we actually estimate those elasticities once we develop the models? That's where we do this called model perturbation, right? Or you can call it permutation as well, right? But we call it model perturbation, where all you do is you build these random forest models and you predict units off of different price levels. So for each product, or maybe channel product, or customer segment and product, right? You create these artificial price points within the bounds of observed price points that you've seen in history. So you create some artificial price points, 5 or 10 price points, and you run predictions on each, right? And so as you run predictions on these simulated price points, you may get something like this little table down on the lower right side. You have some simulated prices, you have predicted units, And you simply calculate the implied elasticity, right? So you'll have an implied elasticity of 1.04 when the price range is between $400 to $500. You have an elasticity of 2.38 negative, right? When the price range is between 500 and 550 and so forth. That's sort of the logic behind that. And so that allows you to have these price range dependent elasticities, which you can get through linear regression, but this tends to be a bit more accurate using machine learning models, right? So that's the idea. And we'll do that together. We'll actually run these random forest models together. We'll run the perturbations and you'll see what that looks like in practice. Okay, good. Let me close this one out and let me actually share the code, and we'll start right off the bat. For those of you that may not be familiar with R, or maybe you're familiar with Python, we'll do a session in Python in maybe 2 or 3 months, just so we kind of cover that as well. If you have a tough time seeing, just let me know in the chat. I try to enlarge this so you guys can see, but this is where we actually do the coding exercise together, right? And the webinar was sort of intentional. One of the reasons I wanted to do this is I remember when I was a pricing practitioner, and especially earlier on in my career, like I managed a pricing team, but I was doing pretty heavy analytics, and there was just not enough resources that could actually show me how to estimate price elasticities. And there was bits and pieces on throughout the internet sprinkled out, but there was not that kind of unified resource that I can go to and observe different methods that I could estimate price elasticities by industry, by situation, and things like that. So that's my intent in kind of doing these webinars, is actually showcasing, give you a flavor of how to do it, give you the code, hopefully kind of give you some content that'll help you with the concept. And hopefully you can actually take this and lift it, put it with your own transactional data in your companies, and try out some things, right? So that's really the intent behind me kind of having these sessions. Okay, let's get started. Okay, so fictitious company, imagine you're, doesn't matter, but imagine you're a manufacturer or a distributor. You're going to be selling some higher priced equipment. Pretend it's for, I don't know, pretend you're a distributor selling to restaurants, right? And these are higher priced equipment that you're selling, right? So this is not consumer products, not candy, but think of more along the lines of like refrigerators and ovens and things like that. Okay, just to get you a sense of the price ranges that you'll see in the sample data. So we'll load some libraries. Let's actually do that. I'm gonna do this real time, and hopefully it's not gonna bug out on me. For more complicated models, I've already ran those models and saved them, and we'll sort of invoke it into the screen. I'm using RStudio for those of you that may not be familiar. And again, looks pretty simple if you're using Python as Python notebooks. I mean, similar sort of structure or flow at least. But let's do some baseline functions. I'll explain what these do. This is where I'm basically kind of specifying some things. As I'm running the price elasticity models, like what sort of limitations do I want to apply for the data, right? So one of the limitations that I'm going to apply is I want at least 26 weeks of data, right? And working with the weekly data, I want at least 26 or half a year data. I want to have at least a 5% variation in my data. Why? Because if there's no price variation, it's really hard, next to impossible to estimate price elasticities, right? The number of simulated price points. And again, this is sort of heuristics, but I just said 5. There's more scientific ways to do that. But when we actually run the perturbations on the random forest model, I say, let's just create 5 simulated price points for each sort of product instance, right? You can change this to 10, et cetera, but it's going to divide the range evenly, right? So if you're putting 5, it's going to basically divide the price range into quintiles. If you put 10, it's going to be deciles and so forth. So starting year and ending year, I'm basically saying, hey, let's filter the data out that is before 2018. And then I'm doing some random functions. I'm not going to go into the details, but I'm doing some functions that create some variable importance plots that we'll use later on, that create kind of measure the root mean squared error, which is a measure of the accuracy of our model, and we'll do that by product group. So all these random functions, including week of month, and including some function that is going to clean some messy text. So notice I ran that down below. Okay, now it's time to actually pep our data. So let me show you what the data looks like. We'll read it in. And again, this is this is simulated data, right? So pay less attention when we get into the specifics of the model, what the data looks like. But let's see what this looks like in practice. And so that's all we have, right? So we have customer class, we have a product description, we have a week date, which is the week ending date, we have sales dollars and units. That doesn't matter what the customer class says, but GPO is just, it's a group purchasing organization. It's pretty typical in sort of manufacturing distributor environments, right? They typically tend to be the largest customer because they're essentially buying huge bulk purchases for their own customers. And we have other customer classes. I believe we have restaurants and we may have institutions, which is sort of universities, prisons, and things like that, right? We'll do some calculations. So notice I'm converting this to data, measuring the average selling price. I'm also measuring things like the price ratio versus the median price ratio versus the mean price. Why? Because you could theoretically build your price elasticity based on that, right? As opposed to your absolute price, you're now building it off of this ratio relative to the historical median and average price. So let's run these formulas real quick. So at least we have the pricing variable included. And let's do some exploratory analysis. So let's just see what the data looks like, and let's just look at the seasonality and things like that, right? But one of the things that I'm doing is basically I'm limiting my data set. I'm limiting my data set only to those that meet my threshold. So again, 26 weeks of data at least, price variation of at least 5%, things like that. So let me run this code real quick. And again, just for the sake of this exercise today, so it kind of goes faster as opposed to running, 150 products. Let's just focus on the top 10. We'll make it a little bit simpler. So we'll filter our data for the top 10 products. So notice this. But let's look at seasonality real quick. And again, this is based on the raw data. I just want to be able to see what sort of variables do I need to create, right? We're going to create some seasonality variables. We're not going to use the week ending dates. We're going to create some indicator variables, right? Ones and zeros, they're called dummy variables. But this is what it looks like based on the raw data. So the last sort of 3 or 4 years of history, weekly unit sales, you can kind of notice some spikes. It happens to be a spike, I don't know, mid-January, maybe February timeframe. And maybe towards, I don't know, towards the end of the quarter, or maybe mid-quarter, there's also spikes, and then towards the end of the quarter it goes down. But let's actually see what our seasonality curves will tell us. We can use a package called Profit. Facebook developed it, but it's a really elegant package. That coupled with kind of the forecast package in R tends to be the probably go-to libraries that people tend to use for time series analysis. So what we'll do is we'll actually do an analysis of the seasonality of this data. We'll do it in a fairly statistical way, and I'll explain what this does, but let me just sort of run this code in the background. And I know it's quite a bit of code, but let me just run this real quick, and I'll show you what this looks like. Okay, and I'll explain in the meantime what this does, right? So we're going to take our data as it stands right now. We're going to create a training and a validation set. We'll take 70% of the training data and put into, or 70% of our data put into training data, and we'll put 30% into our validation data. And what we'll do is we'll create these sort of seasonal patterns using what's called Fourier terms, right? And so Fourier terms are nothing more than using sort of sine and cosine functions to create these cycles and model these cycles on the data. And what this kind of loop does, that I'm looping through different Fourier terms essentially, right? Do I use 2, 3, 4, 5, all the way up to 30? What this does is simply tries to predict unit sales using different Fourier terms, and it basically looks at like which one has the lowest validation error, right? And whichever has the lowest validation error, I'm going to pick that one, and I'm going to now predict unit sales on the training data and just showcase the seasonality. Basically, what the model told me is the seasonal decomposition of this particular data, and that's what you see on this screen. So this is, again, taking out all the noise, taking out the trend, and collapsing all the years into sort of one weekly sort of seasonality throughout the year. And so this is where it really makes it clear, right? Again, sort of maybe this is not mid-January, maybe this is like a February mid-February timeframe, a huge spike, right? For whatever reason, let's pretend it's an industry thing where people tend to buy a lot of stuff in the beginning of the year. We're serving restaurants, let's say, right? Maybe that's a way for them to prepare for that year and buy a bunch of equipment, right? And then you tend to see a dip. You tend to see a dip towards really at the end of the quarter, the start of the new quarter, right? You tend to see kind of a dip down, but for the most part, there's this nice cyclical element where sales go up in one month and really go down in another month, right? So we'll make sure we include that in the model and create some variables that account for that. Okay, so let's just kind of proceed with our code. So we'll visualize the seasonality, right? We'll create the modeling data set, and so notice I'm doing some additional things here, right? I'm creating a year variable, creating a quarter variable, creating a month variable, week of month, right? Maybe there's something going on in the last week of the month, right? Maybe there's something going on in the last month of the quarter, and we'll create those variables as well, right? But that's what I'm doing right now. I'm also going to create the lag unit sales, right? We talked about price elasticities is nothing more than just creating a pretty strong demand model, and we're going to estimate price elasticities off of that. So that's why we want to make sure that we have a pretty good, pretty robust demand model given the data that we have, right? Which is fairly limited, right? But I'm creating some lagged variables, some lagging units by 4 weeks, 13 weeks, 52 weeks, right? So let me just run this real quick. Perfect. Okay. And we talked to the internal experts of this company, right? And in this case, right, you're going to talk to your internal experts, your coworkers, right? And the sales managers and and I don't know, the marketing people said, well, our customers really tend to finance our product really heavily. They tend to buy more stuff when the interest rates are lower, and so you may want to include that in the model, right? So we said, okay, fine. Let's see if that is meaningful. So let's actually include interest rates, public data. So we pulled it off of the Fed site. So we'll include interest rates, and we'll put that in the model. Okay. End of quarter period. So notice in the seasonality, we saw those dips, right? And it was hard to tell when we thought it was sort of towards the end of the quarter. So we'll create some variables. We'll create end of quarter variables, end of the first, second, third quarter, and so forth, right? So that's what we're doing in this step. Perfect. And we'll join it to our model data. Great. And let me just kind of give you a flavor maybe of how this data looks like. So let me see if I can do this real quick on the spot. This is a model data. Let's say 20. Perfect. Okay. So that's how our data looks like right now. Remember where we started? We kind of started with this section. We added average selling price. We have year, quarter, month, week of month. We have some lagged variables for the units. We have interest rates, and we have this sort of character variable, right? That says, is it, what is it the end of the quarter? Is it the end of the first quarter, et cetera, right? So again, we'll use this as part of our modeling effort. Okay, good. So let's proceed real quick. We'll convert the units and price to log scale. We're not going to use this in the first model. We'll use this in the next model. And again, why we do that? Maybe I can just explain it now. So a couple of things. One, there's some really sort of helpful properties by putting units and price on a logarithmic scale. It really helps with outliers. So if you have really high outliers in your data, converting them on a log scale helps, right? It helps the model. It just sort of compresses that data range. That's number one. Number two, which is probably I think the most important for practitioners, which anyways they just convert it into a log scale, is once you convert both of these variables on a log scale, the interpretation of the coefficient now moves to a sort of an elasticity coefficient or a percentage based impact, right? So as opposed to the typical linear regression coefficient, which is, let's suppose your pricing coefficient is 3, which means if you're increasing price by 1 units, increase by essentially 3 by 3. This one is going to be a percentage change, right? So this is going to be if you increase price by 50%, your units are going to decrease by 3 times 1.5%, right? So that's kind of the intention behind converting things on a logarithmic scale. Okay. We'll create some dummy variables for the time indicators. And why do we do that? We don't need to do this for a machine learning model. We'll do this for the linear regression model just to make this a little bit easier. So all these variables that we created for year, quarter, month, week, and month, we're going to create some dummy variables, ones and zeros essentially, right? Okay. Now let's actually look at what this data looks like and sort of what the relationship between price and units are. So I'm going to pick a product. Let's just do this for one product, and it's a bunch of code for those of you that may not have worked with R. This is for the most part, I'm using the tidyverse packages, tidy models for the modeling effort. I'm using ggplot for the visualization, right? Ignore the warning signs, but this is roughly kind of what it looks like maybe for one of the products. This is on a log scale, so notice a fairly linear relationship. There's a couple of lines put over the plots, right? You see the price points on the x-axis. You'll see log of units on the y-axis, and again, even the price points are on the log scales. This is likely in the thousands, but you'll see it by customer type, right? So you have GPOs, institutions, you have restaurants. So fairly linear relationship for the first couple, maybe even for this one, right? There's a couple of outliers that are skewing things, but this is the kind of the fitted linear regression line in the absence of any other kind of variables, right? This is more of a smooth sort of a curved line. So that's based on the log scale. And if you want to look at the kind of the normal scale, that's what this looks like. Again, similar patterns. The only difference is notice kind of on the log scale and the log graph, these outliers, right? They're a little bit tighter, right? Because it's on the log scale. So again, fairly linear. But if we look at another product, maybe I think it was product 6. It looks very different. And I think that's why we tend to favor machine learning models when you have this high sort of non-linearity in the model itself. So again, this is based on the log scale, right? So if you look at restaurants, you can't really say this is a linear relationship, right? Again, at least not based on these kind of two variables that we're trying to visualize, right? You kind of see this this hump, right? This curved line over here, right? Institutions, we don't have enough data, but for GPOs, right, it's again, maybe you can make the argument that it's linear, but there's some non-linearity to this as well, which is, again, one of the reasons we may want to use machine learning models, okay? So again, quick visualization of the data just sort of helps you confirm, like, how effective is my linear model going to be when I use it on the data versus do I need to do any transformations? Do I need to use some other modeling method, okay? So let's do the modeling, right? So we'll kind of start with a couple of things. We'll actually split our data into a training set, into a test set. We'll train the model on the training set. We'll evaluate its accuracy on the testing set. I would say in most instances in industry, folks don't do this with elasticity models, right? They just sort of take all the data, they train some model, measure the elasticities, right? Which is okay. I mean, directionally, I think it's okay. A lot of regression models tend to heavily overfit. You really want to measure the accuracy. You want to try a couple of models and see which one is more accurate on the training data. But notice we're actually splitting this on the time. So we have, I don't know, 3-4 years of data, maybe 4. And so we're going to take 75% of the data, put it into a training set, 25% putting into a test set. And again, we're splitting it by time. So there's sort of a clear delineation. We're trying to see how the model performs and predicting demand on the unseen data. And then we'll estimate the elasticities, okay? So let's actually split the training set. We're using the tidy models package here. But one of the first things we'll do is we'll do linear regression, right? So we'll do this multilinear regression. The method that we're going to use is called the midpoint method, right? Which is probably the most basic way of measuring price elasticities. And it's good enough, I would say, right? If you're trying to get some quick insights, if you're trying to get some scenario analysis or maybe some segmentation of your customers and your products based on price sensitivity, I'd say it's a good enough method. But let's actually do some variable importance. So for variable importance, to figure out which one of our variables are the most important in determining demand, right, beyond pricing, we can run just like a sort of a basic random forest model, right? And it's actually an appropriate thing to do, like running a basic random forest model first, observe the variable importance, things that are not that relevant, just exclude it, and then run your regression model, okay? that's sort of an accepted practice that you can do. So let me run this code real quick. I'll explain what this does actually for just maybe for those of you that are curious and may not have sort of used this, but data models is like the kind of the newer version of the R modeling ecosystem. It puts things in a very sort of structured, workflow environment, right? So we create some, we call it recipes, but that's really it's really a way for us to kind of step through iterations of the modeling process and specify things like removing variables, specify things like creating dummy variables, and doing things like this one particular step. What this does is if suppose the training or the testing data in our case, right? Suppose it doesn't have certain categorical variables. Why? Because we're splitting it based on time, so you may not have a certain year or maybe a certain customer that's a recent entrant is not included in the testing set. It basically creates on the spot, it creates these dummy variables that are not present in your testing data. So that's sort of what you're doing here. And then we're going to prep our data, and we're essentially going to convert it into a format that we can use and ingest for modeling. So notice down here. Let me actually do this instead, so you can see this a little bit clearer. But if you look at this, this looks very different than what the initial data that we sort of put into our screen, right? So we have average selling price, right? We have lag units, we have interest rates, we have indicators for the years, we have indicators for the months, and we have all these other sort of time-bound indicators that we thought were relevant after observing the seasonality pattern. We have units. And notice what it did, right? So customer segments and product groups, right? It created dummy variables. So these things were just sort of characters, right? These are individual columns, one for customer class, one for product group. So all we're doing is we're creating these sort of dummy variables here, okay? And why do we do that? We do that for a random forest model to actually determine which variables are most important. So let's build a random forest model. We'll do that here. We'll first of all, we'll tune the model. We'll do an automatic tuning for now, based on this sort of a manual grid that we're going to specify. I'll explain what this does, but let me just run it real quick. So what I've done here, right? A couple of things. One, I've specified for the random forest model to do 3 things. One, figure out what is the optimal M-try, which is one of the they call it hyperparameters for machine learning models. For random forest, and I apologize for the lack of preparation. I'm doing this webinar sort of real time. Random forest M-try, I believe, is the number of random sort of variables that the algorithm is going to try to sample from, right? So if you have 50 variables, you're basically specifying here that like, hey, sample like from 20 of those, or sample from like 10 of those, right? And it's going to randomly select 10 columns, and it's going to sample the data from there, right? So that's really what this does in practice. Trees is the number of trees. Recall, we've talked about random forest being nothing more than a collection of decision trees. Here we're specifying how many trees do we want? Do we want 500, 1,000, 1,500? 500 is typically sort of a good baseline, right? Min n is I believe the sort of the minimum number of data points per sample that we want to include for a particular variable, right? So if the model is going to select, let's say, the pricing variable, and recall those decision trees are splitting off into branches and things like that, right? We're specifying like, hey, random forest, you need at least like 5 data points in there, right? Otherwise, it's too little, right? So all we're doing is we're sort of optimizing what those hyperparameters should be, okay? And we created a grid. Let's just kind of look at how the grid looks like, right? All we're doing is we're passing this grid off into the model, and there's certainly some levels here, like how many random variables we're going to split, how many minimum data points that we need, and how many trees, and there's like, I don't know, we're trying out like 64 options, right? I've already ran this, so don't worry. This will typically take you, I don't know, 15, 20 minutes to run if you have a decent laptop. But I'm just gonna kind of read it in after I run it. I'm not gonna bore you with this graph, but basically what this shows is the root mean squared error of the random forest model that we just ran, and basically what it is given certain variables. And so what we've seen here is the most optimal setup is, when your random variable number is more like 5, and I think the minimum number of data points is 5, right? It's a fairly sort of constricted, compressed data set. It sort of makes sense. We're going to choose the best model. So of the model that we optimize, we're going to choose the best model. And again, fairly simple command lines, like select the best model based on RMSE. So that's what we're going to do. And we'll run the model, right? So let's actually look at what that looks like. But to actually run the model, but it's fairly simple, right? You're gonna set the random forest engine, and you're gonna fit this model, which is nothing more than units, predict units off of these other variables that you've seen in the data. Permutation is just I'm not going to go into the details, but it's a way for the random forest model to essentially determine which variables to randomly sample as it's running the iterations, right? And so what it does is it permutes, right? It kind of changes the value of the different variables that you have, and it observes which of these changes have the biggest impact on accuracy of the model, and whichever changes have the biggest impact, it basically says like, hey, that's a really important variable. Like, let's actually assign a higher score, right? So that's really kind of what it does in theory. But let's visualize what this looks like. So again, we ran the model. Let's look at variable importance. It's on a relative scale, so put everything on a relative scale of 100. But product group is important. This particular product, it basically says like, hey, when this product is there, it's really important to predict units for your company, right? Because we didn't do this model by product, we ran it for your entire company. It's 10 products, but in theory, you can put in your entire product set. Lag units is important. Things like average selling price is of course important, but notice it was the second or the third most important. And for some products, it may not be that important, which is typical in B2B settings, right? Like, if you ask most salespeople, they're going to say, it's really important. Price is very important. If we increase price, we're going to lose the business, right? For many products, again, especially in B2B settings, especially when you sort of get into industrial products that are financed and things like that, price is often like the fourth, fifth, sixth most important thing, right? So here in this case, it was the third most important thing. And customer class like restaurants was an important predictor and so forth. You can kind of go down the list and see the rest, all the variables. I think we may have, I don't know, 100 or so, just based on these dummy variables that we created. So what we're going to do is we're going to let me actually see what my code says. We're going to actually exclude variables where the variable importance is less than 1, right? It's an arbitrary exclusion, but for now, I want to limit my data set when I do my linear regression to only those variables that my random forest model said, like, hey man, you should really stick with these, they're important. Okay, so that's what I'm doing. Let me actually run this real quick, and it's going to automatically limit my data set, but it's going to exclude a bunch of variables that the model said it's not important. Now, let me actually run the correlation on those. And I want to sort of visualize what the correlation looks like. It's a bit of an overkill, but I like to do that with linear regressions, and I'll show you why. Let's see if I should run this one more time. It's a little bit clunky. Okay, perfect. So let me show you the output. So we ran a correlation plot that doesn't want to display correctly. So perhaps I'm going to do this. No? Okay. Either way. Let's run the code one more time and see if that changes things. No. Okay. It doesn't want to cooperate in the higher resolution. But what it does, so just use your imagination on this busy plot, but it basically measures the correlation for each of the variables, right? And so highly correlated variables, we'll have sort of this darker shaded cells, we'll have larger circles. If it's a positive correlation, it'll be red. If it's a negative correlation, it'll be red. And so what I'm trying to do is I'm trying to figure out which variables to combine, because they're really highly correlated with each other. And so I know it's hard for you to see. When you actually run this code on your own, it'll be a nice display. I just have the I saw the resolution increased on my app, so it kind of messes things up. But if you notice, like federal funds rate is really highly correlated with certain years, right? Like 2019, 2021, right? Which makes sense, right? I mean, you have substantially lower interest rates in some year than others, right? So maybe there we can exclude some variables, right? And in fact, we can probably exclude the federal funds rate when we run our linear regression, okay? And notice that units, lagged units are highly correlated with each other. Like it's not a surprise. We know that lagged units are correlated with unit sales. And so it's not a surprise that other lagged unit sales are going to be correlated with each other. And so notice the 52-week lag, 13-week lag, et cetera, is correlated with the other. So we'll combine it, okay? Well, let's do that. Let's just combine it for the linear regression model. And let's run a model, right? So we'll run a very simple model. Notice like we're kind of taking out these 13, 4-week, 52-week lag units. Why? Because we've combined them into sort of this average lag unit variable. Let's run our model. And it looks a little bit different than maybe what you're used to, right? All we're doing is a couple of things, right? Well, we're taking the training data and we're essentially grouping things by product group and customer type or customer class, right? And then we're nesting the rest of the data, right? So you don't have this like big, huge sort of data frame. You just have products and customers and you have nested data underneath, right? And so I'll show you what this looks like roughly, right? But here's your product group, here's your customer class. And our data, our details, all those, pricing, units, and dummy variables, and et cetera, they're nested here, right? We're left with 14 variables, including units, that we're trying to predict, right? And what this code did, it actually ran the regression model, right? We said let's predict units off of all these other elements. Notice we excluded things that were highly correlated with each other, and we only use those variables that the random forest said were pretty damn important. And so what it does is it runs the model and it automatically creates these sort of nested elements where you can look at how effective was the model, what was the adjusted R-square. We can look at p-values, even though p-values are sort of controversial nowadays, but we can actually do these things all at once by product group versus having to do this on a kind of a massive data set or having to do some kind of a looping thing that people still sort of use. So let's look at how effective our model was, right? Here's our model stats. And again, simple command to look at the model summary. And so we'll have our product group, customer class, and this R-squared, adjusted R-squared is basically a measure like how good was the underlying model for each of those levels, right? And so higher the adjusted R-squares, typically the better. Lower the AIC value, typically the better, right? And so you can kind of get a sense for how good this model was, right? Like for product VZ, institutional customers, yeah, it did a pretty good job. Sorry, I'm looking at the R-squared. The adjusted R-squared is not that good. For product FF and restaurants, it's about 0.5. And then others, it's much lower, right? So leads us to believe that there's other variables that we haven't sort of included, but it's okay. It's not bad. It's not unusual for sort of regression models. Let's actually look at the model accuracy on the training data. And we'll actually do that. We'll do that not for the entire data, but we'll do that by product and customer, right? We want to get a sense for like how good was this model on the training data in predicting unit sales by product and customer group. RMSE is your root mean squared error. It puts the errors at the same scale, the same level that your units are, right? And so we'll get a sense for how meaningful that is at the end when we actually look at the average weekly unit sales. But like the RMSE for product A for restaurants 14.8, for GPOs for this other product was 2.33. We don't know how good or bad it is until we see what the average weekly sales are, right? That's where you can also use things like MAPE or some other measure to look at accuracy, right? Let's look at the coefficients. So this is the modeled coefficients. You have products, customers, and you have the coefficient for the price. Now notice this is just not on the log scale. This is just purely on a kind of a normal regression scale, right? It's your pure sort of multiplicative type coefficient, right? So if your coefficient here is negative, what is it, 0.00334, right? If you increase price by 1, units are going to go down by this times 1, right? Or if you increase price by 5, et cetera, et cetera. Why is it so low? Because these are expensive items, right? Keep in mind, like some of these are thousands of dollars, right? So more meaningful way to look at this would be like increasing pricing by $500, multiply 500 by this coefficient. That's going to be your unit impact. But that's not elasticity, right? Like we're interested in elasticity. We're interested in a number, right? A number that tells us if we increase or decrease price by a certain percentage, what is the percentage change in units? So that's where we're going to use the midpoint formula. And so I'm going to do something else here. I'm not going to go into the details, but the point being, if you're using other coefficients, especially interaction items, you want to put these next to each other. And so that's what I'm doing. I'm just sort of helping out those of you that may want to use this code in your companies and include some other variables, other pricing variables that you want to measure elasticities off of. But let's actually estimate the elasticity off of the midpoint formula. And so I explain what that does. It's a fairly sort of classical way to estimate price elasticities. It takes the mean of the average selling price in the observed training data, divides it by the mean of the average units in the observed training data, multiplies it by the pricing coefficient, right? It's as simple as that. And you get this sort of static singular elasticity number, right? And this is the output, right? So you'll have product groups, customer class, and this is the elasticity. And it's not sorted by anything. I think it's just maybe alphabetically by product group. But you'll see for this product in restaurants, the elasticity is -2, right? For this other product in restaurants, it's -0.6, right? Again, like these low elasticity numbers, not unusual, again, for larger ticket items, particularly if they're financed, which these are, right, in theory. And so, okay, good. So that's our elasticity based on the midpoint formula. We can also see what the performance is on the test set. So let's actually do that. This is a step that I think many companies, I think, including I think many sort of consulting firms miss, right? Is they miss sort of evaluating like, well, how effective is the model when a test that we're actually using to estimate price elasticities, right? People typically just sort of run these models all at once. So let's actually do that. Let's predict, let's use our model, predict it on the test set. That's exactly what we're doing. I think the prediction is somewhere here, right, down below. Notice I'm using this formula to apply the prediction on the groups, on the nested data elements, okay? Ignore the warnings for now. I think it's because like one of the years, maybe it's all zeroed out for the test data, or multiple years because it's only 2022 and on. But let's actually look at the performance summary, right? So this is what the performance summary looks like after we predict it and use our model to predict it on the test set. We have a product or customer class. Here's the elasticities, and here's the RMSC, so the root mean squared error for the training data. Here's the root mean squared error for the test data. So you can use these and get a sense for like. Oh, and by the way, here's the average units, average weekly units, right? So it gives you a sense for like how good or bad of this model is. I'm going to compare the RMSC to the actual average units, right? Like the practical interpretation is for this first line is the RMSC for the training set was 20. The average units on a weekly basis is about 20. So it basically predicts units in like plus minus 20 swing. I mean, roughly, right? Which is not good at all. But it's also not unusual, right? Like you have some sort of manufacturing and distributing setting where even sophisticated forecasts produce some crazy error rates when you go down to the individual customer segment and product level, right? But that's what this means. So that's one thing to pay attention to. How do these numbers compare to the average units? The other thing to pay attention to is how does the RMSC compare on your training versus the test set, right? If this number is much lower than this number, well, there's some overfitting going on, right? Well, I mean, there's some overfitting going on maybe for some products, not for others, right? So I can't necessarily tell that there's heavy overfitting. I think it looks fairly reasonable from what I can tell, right? So not a cause for concern. Okay. Now, this was the good approach, which is not really a good approach. It's a basic approach. It's an okay approach, right? But we call it a good approach for the sake of this exercise. We'll go through the better approach. This is where we actually do a log regression. We talked about that. I talked about some of the benefits earlier, right? It normalizes our data. One thing I failed to mention, it also helps with things like heteroscedasticity, which is when the variance of your data sort of increases monotonically as opposed to it being consistent. And we talked about outliers, right? But again, most often industry practitioners use this log regression because it's a convenient thing because the coefficient that you're getting is actually the price elasticity coefficient, okay? So we'll do the same exact thing that we've done before. We'll repeat the same exact exercise. We're sort of nesting our data. We're applying the model using a function. Notice the function here is log units. So we're predicting log units off of log price and some of these other variables. So let's do that. Okay, perfect. So notice similar output, right? You have your product group, your customer group, you have your nested data. This is where the data is, or you're predicting on. And you have information about your model. Your actual model is sort of embedded in there, your coefficients, the model summary, etc. Okay, so let's look at some of the statistics. You know, and some of it is better than the other one, right? If you look at the adjusted R-square, you see some, you see some decent numbers, right? But overall, maybe fairly similar as the other one. I think maybe the AIC values are more reasonable, right? Let's look at the accuracy on the training data. Okay, I think these numbers are somewhat lower than the previous regressions. We can say it actually improved the model, but we can compare the two. So again, product, customer, and the RMSE on the training set. And now let's actually look at the elasticities. So this is where I said log, sure, there's like some statistical properties and why it's better. But there's just like this convenience factor that people use it. And so the actual coefficient that you get for the price variable, or the log price in this case, is the actual price elasticity, right? And so the way you interpret this now, this estimate, right, or the coefficient is if you increase price by 1%, your units are estimated to decline by 1.18% or 1.2%, right? If you increase price by 2%, your units are going to decline by 2.4%, right? So now this is your actual price elasticity coefficient that you can use. There's your p-value, so you can kind of get a sense for like how reasonable this is. Again, p-values are not as it's widely accepted. They're not as relevant today in terms of determining whether it's appropriate to use something for predictive purposes or not, but it's still kind of a good parameter, right? Like if the number is really high, then it's not really a coefficient that can be trusted. But if it's in the 0.1 range or lower, it's sort of acceptable. Okay. Good. So we've done the elasticities using this sort of log method, which is a slightly better method. Let's actually look at there's one question I'll address it real quick. Let's actually look at the performance on the testing data. And we'll compare the models that we've done for both efforts, and I'll show you side by side. And so somebody's asking, like, how do you interpret the positive elasticities? You don't. Notice one of the things that I've done is I've sort of created these nulls out of positive elasticities, right? So I said ignore it. Don't use it. The reason I tend to do that is, in practical terms, right, it's sort of unreasonable to expect, right, that if you increase price, your units are actually going to increase, right? Again, exception are certain industries, most notably the luxury industry, luxury products industry. But in sort of normal instances, it's always going to be a negative number. And if it's a positive number, it's due to sort of other things that we haven't included in our model, right? And so great question. For now, I'm just sort of zeroing it out and I'm assuming like, hey, it's inelastic, right? It's a better assumption than keeping the positive elasticities, right? And again, the reason you get it here is we're working with a limited data set, right? It's kind of a simpler exercise. Ideally, what you want to do is really sit down with the internal experts and salespeople, marketing people, supply chain folks, and really try to gather as much data as possible to sort of estimate that. That's maybe a slightly longer-winded answer to your question. The other answer to your question is using something like a mixed effects model will do a much better job of not creating these sort of positive elasticities if in fact a product for one of the segments is negative, right? If it's reasonably negative, then using mixed effects models will tend to assign the same sort of range, right? Because all it does is it varies the coefficient minimally within groups, right? So it's another way to sort of control this, right? But we're not doing that. We're doing what's called a group-wise regression, where one product can have widely different elasticities by customer group, which may or may not be the case in practice, but I think many industries it is, depending on the customer group. And so again, comparison of our two model types, you'll see this is our better model, the log-log regression. This is our sort of good model, the midpoint formula. And again, what you would pay attention to is the RMSE on the training set, on the test set, especially on the test set. And again, like there's a couple of items where the RMSE is higher on this better sort of method. But for the most part, it's lower if you just look at all the other products. And in fact, on a weighted basis, it's actually lower. So it's a more accurate model. Okay. Now, let's kind of cap this off and spend maybe 10 minutes or so, 15 minutes on kind of the best approach. And by the way, guys, ask any questions. I know I went through fast. For those of you that may have done similar exercises in your companies, this makes sense. For those of you that are mostly kind of used to Excel, this may be a little bit too complex. And so again, no question is a dumb question. Ask me that or email me later on, but you'll have access to this after the meeting as well. Okay, so let's talk about the best approach. We'll run a random forest model. I'll put in some notes for you guys, right, for those of you that want to take a look at it. But I personally like this, right? It's simple. It's useful. Using random forest, you don't have to do a whole lot of things in terms of sort of data engineering or combining variables. It does a decent job of handling variables that are highly correlated with each other, does a decent job of handling outliers. And you can be fairly creative with the results, right? Especially if you run these simulations. There's other methods that I think are worth to explore, like things like regularization, applied to a log-log regression, right? That's again, somebody that asked about the positive elasticities. Regularization will help solve this or help course correct it, or can course correct it. Mixed effects models, where you run essentially sort of one model, suppose you can run it for an entire company, where you're applying some variability, right? Some randomness to the coefficients within products or with customers, right? That's still very prevalent, again, for kind of most consulting companies. You can also run what's called the generalized additive models with regression splines. So it's similar to like a regression model, but you're now creating these sort of a spline, or these but these iterative lines or iterative slopes, where it's a linear model within a price range, but it's a different slope in another price range, and it's in a different slope in another price range, similar to what we're going to get as an output of the random forest model, but it's within the context of a sort of a regression model, right? So these are some of the other elements, and I'll create content later on because these are still popular. They're faster. They're not as kind of resource intensive as maybe like a random forest model. But for now, we didn't do that as part of this exercise, right? So best approach. We're going to run our random forest model. You've seen these steps before, right? Like we're specifying what the formula is. We're going to predict units. We're running some transformations on the data. We're going to tune our model. We talked about what these mean. And then we're going to train our hyperparameters, right? And again, this probably takes like 15, 20 minutes on this one. Step number one, notice here, I'm going to do it in 2 steps. One, I'm going to tune the hyperparameters using this, just sort of an automatic tuning. I just told the algorithm like, hey, create a grid of 20 values, and I'll leave it up to you on how you do it. And so I did that, and I was able to kind of visualize in step one, and I'll show you what this looks like. Step one, I was able to kind of visualize. I know it's probably hard to see for you guys. Let's see if I can make this bigger. It enabled me to visualize a couple of things. What is the minimum number of data points, right, to include each split for a particular variable, and what is the kind of the number of variables that we should randomly split in the random forest model. So that's what these dots represent. On the y-axis is the actual root mean squared error, and these are the values for each of these hyperparameters. And so what this allows me to do just at first, right, is it allows me to sort of restrict the range a little bit and maybe make a statement like, hey, when the min n hyperparameter is between 5 and like 15, or like 5 and 20, this seems to be the lowest range. And once you go past 20, it really increases the RMSE on the validation set or the cross validation set. For the number of random variables, it's also kind of like 5 to 20. So maybe I'll focus it on this range. And so that's exactly what I'm doing. At step 2, right? I'm just creating, I'm creating sort of this manual grid similar to what I've done with the early example, right? We're creating a grid, and I said, hey, keep it between 5 and 20, and maybe try some trees between 500 and 1500. I create 4 levels for each, right? So that's what I'm doing. So I'm creating this grid that's about 64 values or so. So you can kind of see the details down below on the screen. But let's tune the model. Let's run the model, and we're going to choose the best model based on these tuned hyperparameters. And so that's exactly what this does. It basically told me that, hey, the best model that performed the best on a cross-validated set on the RMSE metric, right, the root mean squared error metric, which we chose as the determination of selecting the best model. It basically has a sort of 10 random variables to sample, 833 trees, and using kind of 5 as a minimum number of data points per each split for a variable, which is just a low number, right? And you tend to get into like overfitting, but I think again for the sake of this exercise, let's just sort of stick with that. It's ideally you want to have like maybe 10 or 20 for elasticity exercises. So let's actually visualize the variable importance. Again, similar logic as we've used before, and the variable importance is going to be maybe not dissimilar to what we've seen in the past. There's going to be some differences, right? Because we have now a more optimal model than before. But again, product was relevant. Average selling price, notice, is the number 2 most important. It was, I think, number 3 in the previous section. Unit lags are important. Federal funds, the interest rates, federal funds rate is important, and so forth. We can kind of go down the list. Okay. Good. So we have an idea of the variable importance. Let's actually evaluate the performance in a test set. So there's a bunch of code that does that. Actually, not a bunch. There's actually very little code that does that. We actually can see that over here. So it's not that complicated to do using some of the syntax. I believe I made the mistake of doing this real time, but hopefully this will run in like maybe in like a minute. Okay, there you go. It's done. Cool. So it actually predicted, it used the best model that I just flashed on the screen, 833 cheese, etc. Predicted it on the test set and actually calculated the RMSE, which will be here, and I'll show you what that looks like. So again, similar to what we've seen with the regression models, where we have the products, the customers, and we're basically getting at the idea of like how good or bad is the RMSE at each of these levels, right? On the test set itself for the random forest model, and these numbers seems to be, again, like visually they seem to be better than the log regression, which was better than the linear regression. So let's just see overall at the model level how they performed, right? So the better model that we ran, which is right here, there's an RMSE of 38, random forces RMSE of 23, right? So like overall, it's just a better, more accurate model. Okay, so now what we're done is, so we're actually going to train the model on the entire data set, right? In fact, I encourage you guys, even on the regression model, when you train on a training set, evaluate it on the test set, go back and train it on the entire data set, right? It's a typical and sort of an accepted practice to do that. You also want to capture more recency in your elasticity model, right? So that's why you want to train it on the entire test set. So we'll do that on the entire data set. We'll train the model. And again, I'm going to just read in the model that I previously saved because it does take a few minutes to run. So then I'll do that. Notice I'm using my best model to actually just predict it on my entire modeling data set, right? And so I have that. Perfect. I'm going to actually estimate elasticities using this. So recall what we've seen before, right? To actually estimate elasticities using something like a random forest, you can do this kind of model perturbation kind of a technique, right? Where all you're doing is you're creating these simulated price points at whatever level you want. In our case, we want to look at elasticities by customer and product group. And so we're creating these simulated price points at the product group level, right? So that's exactly what we're going to do. We're going to create some artificial price points That is this code. Notice what I'm doing is I'm also sort of excluding outliers. That's what this formula is doing, right? Is I'm basically saying like, hey, just exclude some crazy high prices. Like I don't want to go too high or way too low in my range. Like let's create some reasonableness on this one. And so IQR is just interquartile range. It's like the middle 50% of your data distribution. And again, we're doing this at the product level, right? We're grouping it by product. We're creating these simulated price points. Let me just rerun it real quick. Perfect. And that's what you see over here, right? So you see the product groups, and you'll have minimum price points. You have a maximum price point. And I have a slight correction on the maximum price points. I dubbed it max price 2. But really what the ensuing next few lines are going to do, they're going to essentially take the minimum price point and the maximum price point, which is our price range, and it's going to split it into 5 equal parts, and there's going to sort of stack it one underneath the other. So we can use it for our predictions. That is this formula. I'm using the data table package, which is just faster to do on kind of larger data sets. And so notice that's exactly what it did. We have a product group. We have a test price, right? So we have iterations of prices, 5,400, 6,300, et cetera, and we have a range like 54 to 6,300. We'll use this range to actually inform our elasticities that are price range dependent, right? Okay, perfect. So now the next step is just run predictions, right? We have these customer classes or customer segments. We have our product groups. We have these artificial price points, and we're gonna essentially just apply our random forest model that we optimized and do some predictions. And so that's exactly what we're going to be doing. And I'm going to show you what this looks like. But notice all we're doing is we're essentially joining these simulated price points back to the original data set, and we're essentially running a prediction on top of that, right? And so when we run a prediction, we have predicted units for each of these artificial price points that we created. And once you have price points, once you have units, you can measure the percentage change in prices and the percentage change in units. You can figure out what the implied elasticity is, okay? But this is what this looks like. So notice this is a collection of the original data set. But we have the average selling price here that replaced our original average selling price that was used in the linear regression models. And now notice these are ranges. Everything else has remained intact, right? Why? Because we just want to simulate the impact of the price changes. So everything else in a particular row remains unchanged. So we're basically blowing up our data set by like 5 times, right? We're adding 5 simulated price points. If we're to add 10, we're going to blow it up 10 times, right? And these are the predicted units, right? For some, it's maybe sort of a kind of a weird trend, like prices are lower, but predictions are maybe higher, and so forth. Okay, but good. So now we have our predictions, and now we can actually estimate the elasticities. And so we will do that in this code. I'm not going to go into the detail, but notice. Actually, what is, sorry, I got an error. Product is not found. Oh, got it. Okay, that's fine. We'll just create a sample one. But let's look at what this looks like. Oops. Let's see. Sorry, the benefits of doing this real time. Oh, I'm not getting anything. Interesting. Let's just look at this real quick. Okay, perfect. So I'll go with this example. There's something wrong in my code that I just can't figure out under the pressure of doing a real-time webinar. But notice what happened is we have our product groups, we have a customer class, we have a year, and then we actually have our price elasticities. And we have several versions of the price elasticities. We have a weighted price elasticity that is actually weighted by units. We have an average elasticity. We have a high-end elasticity. We have a low-end elasticity. So basically, this is the range. And this range depends on year, depends on the customer segment, et cetera, et cetera. But that's sort of what that looks like. We can actually estimate the elasticities by customer class, by product, by year, and by price range. And again, How do we do that? We do that very simply. We run these predictions using a random forest model, and we run it at different levels, right? And you can choose which level you run it at. And so for us, we actually ran this by product group, by customer segment, by year, and by price test range. So now we can actually have a let's just actually look at one product. Just let me see what the products are called real quick. Bear with me, guys. Oops. Because I do want to kind of illustrate this to you with a real example. So let's just pick a sample product like this one. Okay, perfect. Okay, good. So this is like an output. This is a sample product, customer class. Here's the year. Here's the range. So the interpretation is for this product, for this customer class, for this year, suppose in 2019, the elasticity was negative 0.214, right? That's kind of the weighted elasticity. But really the range was between 0.2 and 0.4 and so forth, right? And so the benefit of doing this modeling sort of an exercise is, one, you can get a lot more creative, right? In terms of at what level do you want to display elasticities, right? Number one. And number two, you can also create sort of these weighted elasticities, weighted by units, weighted by revenue, and things like that. And then, third, it's just a more accurate model, more accurate demand model you can get with linear regressions, right? So that's kind of the benefit of this one. So that is largely the kind of the demo part of the exercise, guys. Part of my snafu towards the end. But again, kind of the intent with this session was, one, just kind of go through some typical methods by which you can actually measure elasticities in your companies. These are fairly simple. Like once you kind of create one sort of a modeling exercise, you can pretty much copy and paste and pour that onto another business unit, other product groups, et cetera, et cetera. But the intent was to just kind of showcase three methods. Again, midpoint, fairly typical, your classical example, showcase a log-log regression, which is still probably the de facto go-to method to estimate price elasticities, and showcase kind of a bit more sophisticated machine learning based method, which is random forest, which again uses the simple idea of creating artificial price points, running predictions on it, and then measuring the implied elasticities by looking at how your predicted units change as the actual simulated price points change in terms of a percentage, right? And so that's what we went through today. You'll have the content that we went through. So I know this is a very kind of a fast, very information intensive session. We had like an hour and change with each other this afternoon, but you'll have the content. You'll also have this code that will be sent out to this meeting. If you have any questions afterwards, right? Maybe you're kind of running this in your company, shoot me a message, but if I have time, I'll respond. I'm happy to help. Okay, good. Christine had a comment. Thank you for thank you for the positive words, Christine, on my ad lib presentation. I think the logical next webinar is to show how to publish these results into an administrative view, such as Tableau or DB. Perfect. Yep, 100%. And in fact, that's exactly, Christine. We're going to use this on I believe it's on January 20th, where we kind of go through a B2B margin analytics dashboard. We'll have some scenario analytics capabilities. And so part of the output of the elasticity exercise will be some elasticity coefficients we can use for scenario analyses. So part of your question will be addressed on that webinar, but I agree, there needs to be like a session where we can actually build like a full form kind of pricing scenario analysis, profit optimization kind of a view, which is, again, to Christine's point, like it's pretty straightforward to do nowadays with tech stack that most companies have. And somebody asks, in your experience, how do you measure if the price changes worked a year later, if the units sold are lower than the predicted from the model? So yeah, thanks for the compliment at the end. Yeah, I mean, I think so doing a postmortem, is definitely recommended. Most often what I've found is reality is always different than the prediction, just because there's just so much variation of what happens to the market. You're sort of A movers in companies, like these are like your 0.5% of your assortment that drives like 50% of your sales, that tends to be pretty spot on, right? Like those tend to have like fairly good predictive power. But I would always, I think to your point in the question, because I think there is an important point in your question, I would always do that, right? And when you actually do kind of an annual price increase, that is based on some scenario analysis that you ran, and you kind of go back a year later and see how units have changed. I think it's a worthy conversation to have, right, with the sales team, and again with the supply chain team, maybe bringing your finance partners to really understand what changed in the market, right, in that year, because those elements you're going to incorporate into your subsequent modeling exercise. Okay.